Now for the next one in line, we are again going to take a sneak peek into the future. And before I say much about it, I would like to invite Pranjal back to the stage. Pranjal Sharma, if you could please come and introduce our next keynote speaker for the session.
Thank you. There are so many types of computing happening that I think it boggles me as an economist, still floundering amongst all the engineers. When cloud computing was introduced, I thought it's really about trying to figure out when the rains are going to happen. But then I realized that cloud computing is a bit more than that. And same goes for edge computing. I thought it had something to do with razors, but it wasn't actually. So it brings me to our next speaker, who's going to speak about quantum computing and quantum technology. So I have the pleasure and privilege to introduce Reena Dayal. We met a few weeks ago, and I was fascinated to learn about the work that she's been doing on quantum for quite a few years now. And I think it's something which is genuinely futuristic. It's also right here in the present. It has the potential for very fundamental shifts in the way computing is done, not just in India, but across the world. So perhaps it'll be important for us to understand what it means, its applications, and how do we prepare for it? What do we do? How do we understand it? How do we equip ourselves to be able to make the most of it? Reena is chairperson in the board of the board and CEO of Technology Leadership. She's in innovation management and culture, future tech and its impact on business and society. She's been an angel investor. She has a focus on the Internet of Things and is a Chevening Fellow as well. So with this, Reena, I think that your work speaks for you more than anything else. So may I invite you for your address.
Good morning, everybody. And I wanted to take this opportunity to thank IET for inviting me, and more importantly, for organizing a Future Tech Congress. We all know the impact that technology has on our lives today. And as we move forward, that impact and correlation with technology is only going to increase. And therefore, the topic of future tech is extremely important. So a big applause to IET for actually organizing something like this. And I'm very happy to be here because quantum is an often misunderstood subject. A lot of people think about quantum as something which is far ahead in the future. And there's a lot of discussion around whether there's a bigger hype than what should be there, or whether it is current technology or tomorrow's technology. So much so that even in the tech sector, when I remember I started working in this space and around a few years ago, and some very senior people that I used to work with actually asked me why I was wasting my career on this, because this would be my grandchildren's technology. And so if you have certain myths, it's okay. There's a lot of confusion in the industry. And opportunities like this help me reach out and connect to people, tell you what is really happening in this space from a state-of-the-art perspective and what we can expect today and tomorrow. If we also examine the kind of progress that has happened in just the last 5 years, you will get a good sense of where quantum stands today and what it can do for us today and tomorrow. So with that, I'm going to be covering these topics. I do want to introduce QETCI. So this is a not-for-profit Section 8 company where we are bringing industry, academia, government, various other associations together on the topic of quantum. We are based on a membership-based approach. And our mission is to enable and accelerate the quantum ecosystem in India. The value that we work on, the value system that we've adopted, is to enable global collaboration in science and technology related to quantum. So we do everything quantum focus. Next slide, please. So the question is, why is quantum relevant now? Why are we having this conversation at this point in time? So why is quantum relevant today? For explaining that, let me go back a little bit into the history of computing. Let's examine the past. What is a computing device? A computing device is anything that helps you beyond the usage of your brain to help you compute faster and better, right? So in that context, the abacus in 2400 BC, when it was first invented, is also a computing device because it helps you calculate faster. And then as time progressed, we made discoveries, we made intentions as humans, which helped us do faster computations in some form or the other. Apart from the speed of computation, what also happened is that layers of abstraction started coming in. So it was not just a device which you could move with your hands. It became something which will do a little bit more than that, and computing started getting more abstracted. But the computing that we know today is classical computing. So right from the big data centers that we have with supercomputers in those data centers to that small device which we carry in our hands, our mobile phone, all of this is based on classical computing and based on semiconductor technology, which has evolved as a standard. This technology is based on Moore's law, as we all understand. And therefore, we've seen phenomenal progress, right? From the big mainstreams in the early stages of the computing revolution, in the early 1900s, we actually are at a stage where, like I said, you have devices which are small, IoT devices, which have tremendous computing power. The phone in your hands has more power than the original and more memory than the original mainframes that were there. So based on Moore's law, we've made a lot of progress. Where are we today? When you look at the semiconductor industry and you ask them, what is the next step? So where are we today? Today we are at 1 nanometer technology, which has been proven to be working by TSMC. And what you see in the market is closer to 7 nanometers. So we are at those minuscule distances where transistors are being positioned at that small distances, and you're able to get tremendous compressed devices with a lot of power and capability. But we do not see the future forward from there, because if you go to shorter distances, there is a lot of noise that comes into the picture, and also you are actually getting into the space where quantum effects come into play, right? So essentially, computing as we know it today is coming to an end. That doesn't mean it'll end tomorrow. It just means that if you look at the researchers worldwide, they have already been thinking about it, and there have been different approaches that have been adopted to see what the next generation of computing is going to look like. So people have been focusing on neuromorphic computing, which is computing based on and inspired by the way the human brain works, molecular electronics and chemical computing, where you use chemical reactions as a way of manipulating information, and quantum computing, which is what we'll talk about today, DNA-based computing, a lot of research as to how the DNA could be used to, because there is a natural manipulation of data that happens in the DNA over extended periods of time. So obviously, what has happened is that this has not emerged as something which is very promising from a computation perspective, but it has been found to be promising from a long-term storage perspective. So, there are storage technologies being built around DNA-based manipulations. Artificial organic brain or wetware computing, where people are trying to work with biological systems, integrated with silicon systems to see if some form of computing could be formulated. Out of all of these, I'm pretty sure the two names that you would have heard about, if you have heard about any of these, is neuromorphic computing and quantum computing. That's because these are the two areas where today maximum investments are happening. And that is because, in general, people believe, qualified people doing research in this space believe that this is what the future is going to be. Out of this, quantum computing has taken a lead. There's a lot more investment, a lot more research happening in this space, and we'll see why that is so. So what is quantum computing and what is its link to quantum physics? Before we get into that, let me just, examine what classical computing is. Classical computing, there's a hardware at the bottom, you have an operating system, you have software built on top of that, and then you have layers of more abstraction, right? Where, somebody can be coding, you could be a user using a program which is written on top of a lot of system software which is sitting on the OS and sitting on a hardware. The basis of computing is built into the physics in the hardware. And the physics that is actually utilized for classical computing is classical physics, which is essentially, and some aspects of quantum physics, but mostly classical physics. The difference between classical computing or computing as we know it today and quantum computing is that quantum computers are completely based on quantum physics. And quantum physics is about the physics of the minuscule at minuscule distances. And that's the stage where particles are both particles and waves. There's a lot of uncertainty with where the particle is going to be. And the definition of physics at that level is no longer deterministic in nature, it is probabilistic in nature. In fact, it's so amazing that if you read quantum physics, you will find a lot of similarity between that and the whole concept of Maya and non-determinism in Indian mythology. But don't get confused, it's all science. That's just a correlation. Being a little bit of a poet myself, I tend to draw. But the root of all of this is deep science. So why should, one is of course, if the physics is so complicated at the quantum level, why are we thinking of it as a mechanism for computing? The reason why we are thinking of this as a mechanism for computing is because it provides us billion-fold improvements. And I'm not joking when I say that. I'll explain what it means to have billion-fold performance enhancements when you have a fully scalable quantum computer. That is one. The second is that when we look at problems which are solved by mathematical equations and algorithms in classical computing, we still have a lot of problems that we have not solved or we cannot solve, despite the huge amount of computational power that is available to us. Many of these problems are classified as NP-hard problems in the problem classification as part of the information theory. But what it essentially means is, let's say today if you want to simulate a human brain, do you think we can do it with all the computing power that we have in this world? Actually, no. Even to simulate a 1 centimeter by 1 centimeter portion of the brain with all the millions of neurons in that space, and to mimic that computation, you actually need a huge amount, a big supercomputer with a lot of storage. And today that is the maximum that has been achieved. So there are understanding the human brain related projects that are happening all around the world, which have massive infrastructure available to them, but that infrastructure is not enough for doing the computation, the simulation, the experiments that are needed to fully understand the human brain. So this is one example of why the current infrastructure is insufficient and quantum computing can hold some promise for us. The other is a certain category of problems. All of you, might have heard about the traveling salesman problem. How do you optimize a route? Let's say if you want to look at DHL or Blue Dart, and the whole problem of algorithmically optimizing the route for the best, shortest distance with the lowest cost is actually a non-solvable problem. It is a problem where you can actually get better and better results as you get more and more compute available to you. In mathematical terms, it is referred to as finding the lowest minima of a curve. And that problem can be solved in a much more efficient manner by quantum computers. So certain class of problems which are not solvable by current computers but can be solved by quantum computers is the reason why we want to invest in this technology. it's a whole new information theory. It's a quantum information theory, and hence, right from the hardware level to the software level, it's a completely new abstraction. When you think of quantum computing, you should think about the beginning of the compute revolution, how classical computing was evolving. So lots of new algorithms to be written, lot of new protocols to be written for quantum communications, and so on and so forth. So here we use the concept of qubits. I don't want to go into technical details. I promise you this is the only slide which talks about qubits, and then I'll get into more around industry applications. Qubits can represent a huge amount of information, and that is the basis for the computing power that becomes available with quantum. For example, if you have 1,000 bits, let's compare with classical. If you have 1,000 bits, those 1,000 bits can store 2 to the power 1,000 values, right? Okay, so everybody sort of agrees with that. If you have 1,000 qubits, you can actually store all the values from 0 to 2 to the power 1,000 simultaneously. So suddenly you have exponential capacity that is available. That number that if you start calculating is a huge number. With just a 1,000 qubit computer, you have information values that can be stored, which is larger than the number of stars in the known universe. So that's the exponential increase in compute capacity that you get. There are also certain algorithms which allow you to do a lot more parallel search within quantum. So for example, when you do a traditional search, you actually look for, there is a finite amount of time and a worst case scenario that plays out for you to be able to find information in a large set of consolidated information. In quantum, it's a two-step process. Because of the nature of uncertainty and the underlying physics, there is almost a parallel process which is, starts off, and in 2 steps you get a comparison and a search results for a very, very large database. It doesn't matter how big your database is. So that sort of creates the basis for computation of a very different kind. So is it tomorrow's technology? Some of aspects of this are evolving, so it is definitely tomorrow's technology, but it's also current technology. This is the nature of the investment that is happening around the world. You can see large countries, small countries, countries around the world have been investing a lot. China has invested $10 billion USD on their quantum program. In India, we announced $1.3 billion investment as part of the National Quantum Mission. And before that amount is being made available, I think there are a lot of other investments that have been happening. Today in the morning, we heard Dr. Saraswat also mention quantum computing as one of the areas of focus, right? So it is definitely something which is on the radar for us as well. And all of this investment is largely government-driven, and a lot of private sector investments largely focused in the US and Europe. So all of the large companies like Microsoft, AWS, Google, IBM, and a lot of new companies, they're all investing in hardware. Honeywell is a big, has a very fully integrated stack in this space as well. And today, a full stack service ecosystem has emerged. So there are quantum hardware players, there are people who are working on the system software level, there are people who are playing in the application and algorithmic space, and also on the services side. So today, if somebody wants to, let's say a bank wants to start looking at, hey, can I optimize portfolios using quantum, using the lowest minima problem, can I do something there? That is doable, and banks have begun to focus on it worldwide. You will see a lot of names here. Do realize that it's a very new technology, not a lot of new development happening, so new names keep cropping up every 6 months or so, right? So this is an evolving ecosystem. This is a look at the top patents coming out of quantum technology related areas across the world. Why is this important? It tells us how research is progressing. You know, what is the focus on research across all of these various countries? As you can see, this is a pretty wide selection. So definitely, quantum is being focused on from a research perspective in almost all the major countries of the world. So where are we with respect to the scalable quantum computer? Today, 2 weeks ago, less than 2 weeks ago, IBM announced their Osprey chip, which is 433 qubits. That number is important, but what is more important is for you to see that in 2017, we were talking about 50 qubits. 2021, it was 127 qubits. Even the rate of progress is accelerating, right? So all the people who said that this is going to be our grandchildren's technology need to go back and reevaluate where this technology is headed based on the progress that we've seen in the past and how we are seeing it right now. This is what the hardware and software worldview looks like. On the left, you have various kind of hardware-based approaches. Because it is a new technology, everybody is not betting on the same technology. So we are looking at photonics-based computing devices, superconducting qubits, trapped ion circuits, companies which are focusing on NV faults in diamonds. There's an Australia-based company called Quantum Brilliance, which is focusing on that as a mechanism for computing. Cold or neutral atom-based technologies, and topological qubit, which is one of the most, this is what Microsoft is focusing on, and it is one of the most exotic science-based, it talks about a two-dimensional particles which could be leveraged for, could be leveraged to create a qubit because they tend to be more stable in 3 dimensions. On the right-hand side is the software ecosystem. So in many cases, the software is sitting on top of an existing hardware. So Google has a superconducting qubit, but they also have a platform called Circu. Same is true for Qiskit is from IBM. They also have a superconducting-based qubit. And TCAT is Quantinuum, which is actually creating software to work with multiple hardware platforms and things like that. And this ecosystem is growing day by day, right? And if I was giving this presentation, let's say 6 months to a year ago, I would not be talking about cold atom technology as being, very promising. But with some of the latest developments, this has also become a very promising approach. So I think from an end user perspective, it does pose a certain challenge. If you want to use the technology, what is the approach, which technology should you bet on, becomes one of the questions. But to address that question, many of the software players are trying to come up with solutions and have already come up with solutions that support multiple hardwares, with the promise that if you will do programming in quantum on their platform, they will take care of integrating with whichever is the latest hardware that comes in. What is the quantum imperative? All this is fine. Why should you invest in quantum? Why should a nation be focusing on quantum? So I would like to put forward in front of you that future economic progress is going to be dependent on quantum. So any nation which decides that quantum is not going to be their focus area is putting their economic progress on the line. With our dependence on technology today, with the kind of systems that we have today, and here's a promising technology which is going to provide the next era of computing available to us, you have to extrapolate and say how economic progress is going to be enabled. Energy, climate, and sustainability. To understand how energy, climate, and sustainability can be addressed, nature is quantum in nature. Nature is quantum in nature, which means that through quantum, we have a better understanding of how nature works, building a better understanding of how nature works, and as Mr. Prabhu talked about earlier, we can integrate, create solutions which are in harmony with nature. A good example is a solution that has been validated today, that fertilizer production takes a huge amount of energy. Nature does nitrogen fixation in the soil with very minimal energy. And that is an efficient process. The process of creating chemical fertilizers, chemical nitrogen, in a factory is very expensive and it is not sustainable. Today, we have been able to, using quantum chemistry based computations, been able to simulate some of the processes that happen in the natural soil. And therefore, in the future, it is possible to create fertilizers using those kind of processes, rather than the processes that we adopt today. And that is the power of quantum. So if we look at this example, quantum has a big role to play in energy, climate, and sustainability. It opens up very different kinds of solutions for us out there. Basic scientific progress. All of the progress that has happened in science, in terms of understanding a universe, the fundamentals of physics reside on two ends of the spectrum. An understanding of how the universe works from a cosmological perspective and what happens at the big level, which is the macrocosm of where we reside, of which we are a very small part. And the other aspect is what happens at the minute level, which is quantum physics. The holy grail of the entire physics community is to be able to integrate the laws that exist at the quantum level and the laws that exist in the larger macro world that we experience, the way we live, what we perceive through our senses. As we make progress, so today we do not understand the universe perfectly. In fact, we understand a very small portion of it. If you talk to any physicist, they will tell you that our understanding is very limited. And in the last, not decade, in the last century, the entire effort of the physics community has been focused on reconciling these two different areas of physics. So if you're not focusing on quantum, you are not focusing on this attempt to reconcile. As we are seeing progress in computing, that is also rubbing off on the physics side. Today, there are actually conversations happening between cosmologists and quantum computing experts to actually look at new theories that might evolve, because by looking at information or information theories that may exist, that may be able to explain some of these aspects interchangeably. So basic scientific progress is dependent on how much focus is there on quantum. And national security, everybody is focusing on quantum. With quantum, today RSA 2048 is supposed to be future-proof for several decades or so. That's what people believe. All the standards for encryption recommend 2048. All critical systems around the world are encoded with RSA 2048. If you cross a certain number of qubits in terms of quantum capability, you can actually break RSA in a matter of a few days, and then in a few hours, and then in a few minutes as you progress. So today, there is a lot of effort happening around the world to actually create post-quantum secure algorithms, right? And various institutes are focusing on that. We are also focusing on that. India also has been looking at that. So national security, issues of national security, if you're not focusing on quantum, then that becomes your entire infrastructure, your utilities, everything, sort of gets related to that. And this is all linked to impact on several other technological areas and scientific areas. So today, if you look at the James Webb Telescope, right? James Webb Telescope, which is, is going to give us a better insight into a lot of the physics and the cosmological problems that we don't have solutions to. The sensors used inside are quantum sensors. So development in quantum sensors is going to impact not just cosmology, is not just impacting cosmology, it is going to change the way medical devices, diagnostic devices work, the way we look at weather, and we look at various other various other phenomena that can be addressed better by quantum sensors. This is the gamut: communication, sensors, quantum computing, and quantum annealers or specific hardware and software integrated solutions for specific problems, right? So essentially, look at the bigger picture, have full-scale computers, and also look at small chips, which will do very specific activities. So today, there are hybrid solutions for high-performance computing, which have quantum accelerators, which can be deployed in the data center for better integration, faster performance, and so on. So I think a lot of alternate ways of using this technology have emerged and are successfully moving forward. A lot of different kinds of problems can be solved. Before we get into all of this, I wanted to share something with you which will give you an understanding of the here and now of quantum. Around 3 months ago, on 15th of August, QETCI launched a hackathon cum incubation effort in India for quantum solutions. We finished that effort and announced the prizes last Friday. We got 128 project submissions, which might not seem like a big thing if you're talking about e-commerce solutions, but for quantum-related solutions, 128 is so big that I got messages from people around the world saying that that's amazing that you got 128 submissions. We had 37 projects where prototypes were completed in this time frame. And many of these prototypes today are around life sciences, for better drug discovery solutions, for better monitoring of the human heart, and very different kind of solutions, for financial services, for quantum security, for quantum communications, and so on, right? So around, and those are solutions which are trying to solve today's problem using quantum technology. So it's here and now. It's no longer a technology for the future, right? And this is an example that I talked about earlier about how nitrogen fixation, and it explains the reason why you can use quantum, because nitrogenese molecule requires 10 to the power 32 bits of quantum classical storage, right? But this can be stored in just 108 qubits, and that gives you the exponential power of being able to simulate this molecule and simulate the chemical reaction with a much smaller computing footprint on a quantum device, and therefore allows you to sort of examine some of nature's processes which were until now inaccessible to us. So this is an example of a quantum sensor which can actually show what is present under the ground at a depth of 1 meter with a much higher accuracy. This is something that has been developed in UK actually. And what it means is it can help you predict natural phenomena better. You can actually understand archaeological systems without damaging, do better excavations. In war scenarios, it can also help you understand where the landmines are, and there are so many different applications for this particular sensor alone, right? So this was my attempt to give you a little bit of an overview of what quantum is, where it is today, and the kind of real-world solutions that are happening and can happen as we move forward into the future. I hope it was useful. If some of this is interesting, please do reach out. There's a lot of material that I can make available to people who are more interested in this technology, so that you can, as engineers, this is something that you should be really focusing on. It is the future of technology, is itself going to be dependent on this, if I may say so. And thank you very much for listening patiently.
Any questions for Reena? If somebody has, yes.
I want to thank you. That's the best explanation of computing, quantum computing I've heard, and I really like the understanding of the applications is really helpful. One worry for me is if you look at the power of a silicon chip or the human brain or whatever, quantum computing, I'd like to know what is the most efficient hardware that exists today, and how does it work? So I think the question is, if you look at where silicon is today, in terms of, I can imagine big quantum computers solving big problems, but do you see a point where we might be using this technology in our phones or something? I'd like to understand a bit more about the hardware roadmap, please.
Yeah, sure. I think that's a great question and something that I omitted to mention. So this is an opportunity for me to do so. If you think of traditional quantum computers like the big systems, you will always see that picture, which is that huge machine, and the chip is that tiny chip sitting in the center of it, and all of this is in a refrigeration unit. And that typical picture emerges because of the fact that there's a lot of noise in the circuit, which causes, and at quantum distances, particles are very suspect to random fluctuations. So essentially, you need to put that whole device into a refrigerator which brings the temperature down very close to 0 degree Kelvin. And hence, it's something which seems like very, unwieldy and unmanageable. In the last few years, there has been progress on room temperature semiconductor-based technology, room temperature-based photonics technology, which have also emerged as promising areas for quantum computing. From a smaller device perspective, the Diamond NV fault center-based computing is also coming out as useful for attaching along with sensors for making better sensors, and also for providing limited compute capability which is focused around those sensors. So like the way forward for quantum IoT, so to say. So there are alternatives which are there. The attempt in the industry, and there are a lot of new players out there, new startups which are focusing on completely new technologies. If you ask me personally, which one would I bet on? I would bet on photonics. Because photonics to me is, and of course I may be biased, India has a stronghold, traditionally on photonics. So I would want this to be, the solution to emerge from photonics. But more importantly, if you observe photons, right, which is light, it travels all across the universe without interfacing with anything, right? It doesn't get, so it is not subject to noise. The challenges with photonic-based circuits are something else. But I feel that if you can overcome those challenges, and we can see symptoms of that emerging, then the scalability is going to be very high, is what I believe. But if you see, if your question is where is the industry progressing most right now, it's superconducting-based qubits. So everybody, if you look at the investor approach, a risk-balanced investor approach, the large institutional investors, they will go ahead and invest in semiconductor, superconducting qubits-based technology, because that's where IBM, Google, and some of the other companies have made a lot of progress, right? So that's how it is.
So Reena is here, so you can take the questions with her, because we are a little delayed, so we'll continue with this. But before we do so, I would request Pranjal and Tony to please come on the stage and give a token of appreciation for Reena.